So if we go through and actually do out the calculation, we can get to two equations which tells us the detected frequencies in terms of the original frequency and then two speeds. Now notice that the equations are slightly different, and this is whether the source is approaching you or receding from you. So this is getting closer, this is getting farther away. So one way to think about this here is the most common scenario is, for instance, that you're standing on the side of the road and an ambulance is coming towards you with a siren blasting, and then as it passes you, it suddenly sounds quite different. A train is another example. So the approaching source is going to sound higher. The receding source is going to sound lower. And notice that that's higher is because this is going to be a number, and usually this number here is pretty small. So it's 1 minus a small number. So if you have like f divided by 0.99, that just makes this a little bit higher. So now be careful. So Vs here is going to be our source speed. So that is, for instance, the speed that the ambulance is going. V is then going to be the wave speed, and that is, for instance, going to be the speed of sound, again, which is what we're talking about. Now, you might then be able to think through the fact that our source speed is typically much less than our wave speed. Our ambulance is not going close to 343 meters per second. Now, you might say, but weird things happen if in fact our source speed is faster. Yes, that's called a sonic boom, and weird things do happen if things travel faster than the speed of sound. And so we don't have to worry about that here. Our sources are going to be traveling slower than the wave that they're making. And remember that again, your wave speed is given by the medium. So again, air, the temperature of the air, the humidity of the air. So these are the results for a source that is moving either towards you or the observer, or moving away from you or the observer. So then, and you kind of assume that the observer in this case is stationary with respect to air, where air is our medium. There are slightly different equations, which has to do with the source being stationary and the observer moving. So in this case, notice that we don't have a fraction, and now this v sub o is going to be the observer speed. Okay, so that's what this is. This is now the observer speed, and so v is again going to be your wave speed in the medium. So in this case, we assume that the observer is moving with respect to the medium. So the observer is approaching the source, or the observer is receding, i.e. getting farther away from the source. So again, you see that there's a lot of parallels. It's just a question of whether you have a plus sign or a minus sign. And again, this number here is going to be pretty small, but we see that if you have 1 plus a pretty small number, this is again going to be higher frequency. This is going to be lower frequency. So you still have the same pattern of higher frequency being approaching, lower frequency being receding, but mathematically the numbers actually work out slightly differently. It's pretty close, but it mathematically is going to be a little bit different. Now, this isn't just a weird effect that you might hear when the train goes by or if an ambulance goes by, but this is actually something that we can apply. So and really the applications come down to measuring speed. One of the applications is measuring car speed. You might know that some police officers have what would be a radar detector, or you might know it called a radar gun. And the idea being that it's actually sending out a wave that then bounces off a traveling object. And when it bounces off the traveling object, that actually changes it's like the object itself is becoming the source, and so you then have a moving source. So based on the frequency that you detect after it bounces off, you can then figure out what the speed of your source was. So that would be one thing with a car speed. And sometimes there are things on the side of the road that also measure speed, but I don't know if they actually work the same way. Another option is measuring storm speed. So you might see pictures of like this, and it's often called radar, and that actually can measure the speed that things are moving again, due to looking at, again, how your radar waves are bouncing off something, creating effectively a new source. So again, there's multiple things going on when you see a picture like this, but one of the ways that they can actually get the speed that clouds are moving is through using the Doppler effect. So recognize that this is a cool effect that based on the shift in frequency, you can actually tell how fast something was moving.